Welcome back, and I hope your one-on-one sessions were productive. We're going to have our last panel. It should be kind of exciting. It's a broad topic. Where are the gaps? Is it up there? Yes. So what's still missing? Where are the gaps in the stack right from the bottom to the top? We have terrific panelists. I think I'll invite them up now to take their seats. I'm going to introduce them. Two of them you've heard, so they'll get a little less of a formal introduction, but again, this is a great opportunity to think sort of broadly. Big data is a huge topic. Lots of technologies are involved. This is our chance to sort of freeform just a little bit. Okay, so let me introduce some folks, and maybe just sort of raise your hand a little bit when I call your name, because not everybody knows who everyone is. Anthony, can you sort of raise your hand? Anthony is the Deputy Division Chief with the National Geospatial Intelligence Agency. He's focused on extensive R&D resources in other areas of LiDAR, which I thought it's interesting. That acronym has actually lots of different ways to interpret it, but I guess the most common one is laser illuminated detection and ranging. He has led several communities of practice forums in data modeling, data engineering, data standards, and support imagery processing architectures. He was the program manager for a number of airborne and overhead collection design and system engineering efforts. He also served in overseas flight operations and OIC for DoD. Mr. Glassy started his career at Hughes Aircraft Company, Space and Communications as a design engineer. So you probably know a lot that we don't want to know, I think.
And I can cook.
Well, that's a good thing. Dr. Jack Collins, Jack right here. You may know Jack from NCI. He's the Director of Advanced Biomedical Computing Center at the Frederick National Laboratory for Cancer Research. Dr. Collins' research focuses on biomedical computing applications pertaining to cancer. His research group develops and applies high-performance algorithms to solve data-intensive computational biology problems in the area of genomic analysis, pattern recognition in proteomics, imaging, molecular modeling, and systems biology. Received his BA from Park College, minor in physics, economics, chemistry and economics, so he's the Renaissance man. PhD in physical chemistry from University of Nebraska. Prior to joining NCI, Dr. Collins worked at SRI International and was also associate at the Molecular Research Institute. You all know who he is. He's been, he's certainly an authority and well known in his space. And I've known Jack for a while. I think I shortchanged you, Jack. There's a little bit here, but we'll skip it for the moment. Jack is well known. Also, from a news section, from the mobile technology section, we have Gary Yao, the head of technology scouting for HTC. Head of technology scouting. What a great title. That's what I want. Anyway, at HTC, Gary is responsible for technology scouting, evaluation, and potential acquisitions. He's located in San Francisco, and he works with the team continuing to explore breakthroughs in disruptive technologies in Silicon Valley and worldwide. The idea is to push boundaries of design to create personal experience for customers around the globe. Prior to joining HTC, Gary had many years' experience in hardware design, semiconductor industry, involved in integrated circuit design, embedded systems, device manufacturing for mobile computing, and consumer electronics. Gary has an MSEE from UC Riverside, received an MBA from Santa Clara University. And the other ones, do we know everyone? So I think you've heard all of the other panelists. So Shane Porter, who spoke yesterday, was the HPC systems engineer at Children's Mercy Hospital, Kansas City, Missouri. Had a very interesting story about using genomic medicine with infants in the neonatal air care, and so did actually one of our other speakers tonight. So it was kind of an interesting health connection throughout. Ron Van Holst, we heard earlier this morning. He's the Director of Research for HPC from the Ontario Centers of Excellence and the Executive Director for Compute Ontario. Again, we heard his speech this morning trying to help commercialize these technologies by bringing together government money, commercial money, and academics and turn that into a real productive endeavor. And who have I missed? I think that is all of them. So the idea here is to look a little bit more broadly across the gaps that remain in big data and the technologies we're using. So what I thought I would do initially, and I have a bunch of questions here, but I thought I would start by asking each of the panelists to give us a couple, 3 minutes from their unique industry perspectives of what they think the critical gaps are. And then from that, we'll start with some questions. And I'm hoping that there'll be a good deal of audience interaction, because this is a chance to maybe go a little bit afield. It's not quite so constrained. And I think I'll start with Jack, since you're center stage.
Okay. So when we first talked about some of the technologies, I think that, first of all, Ron had a great list of questions during his talk this morning. But now, some of the things that we're looking at in big data that are still open problems for us, natural language processing, especially in the areas of new research, where you don't necessarily have the ontologies and semantics worked out. So bringing that together so that we can actually ingest the data, putting that into graph analytics so we can start looking for patterns and that we haven't been able to look at before, especially as we start looking at pathways. And if we've been talking about DNA, but if you start looking at the way that the genome functions and the way that it turns each one of us into the unique whoever we are, there's a lot of feedback loops, and trying to understand that and trying to develop drugs and trying to develop diagnostics for that is becoming increasingly complex. That's a very complex data algorithmic search problem, looking for those subgraphs, so looking at graph databases, and as any of you have done that, that's a memory intensive, pointer intensive problem. So that's not necessarily yet a solved problem. So there's a lot of IOPS involved with there. We've heard a lot about parallel file systems. A lot of those are built for performance, for streaming, but not necessarily for, millions of IOPS per processor hitting it. And then building these automated workflows and pipelines develops even more metadata. And so the data doesn't actually get reduced, it actually grows in many of the cases. And knowing how to integrate all of that and what does this mean, we're looking now at deep learning and trying to take the lessons learned from some of the other industries, that Google and other places, and apply them more into our area so that we can start finding those patterns. And then how do you integrate that? That's still a major problem. How do you get information out, and then how do you get it to a medical researcher who doesn't speak the language that we do in a way that's actionable and it helps you and your health? And just to kind of, something we've been talking about with Anthony here, is we also have a lot of 3D imaging that's going on. I know that Ron talked about the fMRI, but we're doing a lot of electron microscopy, a lot of X-ray and light microscopy, generating automatic three-dimensional pattern recognition inside of those volumes, being able to then search those and crunch those down in a way that we can put them into a database, and then we can start looking at 2D images and be able to pick out 3D objects, is one of those problems that I'm sure that there are folks working on it on another discipline perhaps, and I'm not sure I want to know exactly what they're searching for, but those I think that's an example of where we're all working on a similar technologies in different fields, but the underlying algorithms and the underlying mathematics that we have to do is similar. So I think there's a lot of open problems still, and I would say if I talk to the hardware guys, the speeds and feeds and the interconnects aren't quite there yet either, but it's much more of a known entity.
Well, since you brought up Anthony, I thought maybe we'll go to you and you can tell us a little bit about what you think of the gaps in the way from your perspective.
Well, Jack mentioned the 3D aspect, and we take in reconnaissance data of various types, from video to still imagery to you name it. And there's so much of it now, it's not a dearth of data. And I kind of tell people, think of the Mississippi River at its widest point, and you want to go fishing. Well, you don't take the entire flow of the Mississippi River and put it through a sieve, right? What you want to do is know exactly where the fish is that you want to pull that fish out. And it's not necessarily a needle in the haystack, but it's getting close to that because the volumes of information that we're looking at. So when I was talking to Jack about how to take a 3D volume and look for certain objects from different aspect angles. So if I see a vehicle from a certain angle, I can't determine, is that a car, is that a truck, what type of truck? So I need some type of automatic resource to triage the data to look for that. And I don't have enough people with human eyeballs like we used to do in the old days of, here's my picture, I can look at that, focus in, because I've got another 1,000 images already coming in. So I need compute resources coupled with tools that can triage that data quickly in the 3D dimension, pull out highlighted areas that say, look at this, store the other for later, and here's my priority list. And have that run 24/7. So when the humans come in, it's already stacked up for them to look at highest priority down to lowest priority. And then I have the tools and the analytics to look across different data silos from, say, maybe other partners, pull information out, and get an analysis out to a leader, political leader, a military commander, a group, saying, I know with 92% certainty this is what you're looking for, or this is what's going on.
Right.
So I have to put an error analysis with that. I don't have that yet. I have pieces of that, but it's not elegant, it's not migratable. I see a lot of good tools coming out, but if I step back and put on my program manager hat, how do I brief a non-technical person that I want X amount of dollars over X amount of FIDEP to manage this commodity and push it forward? And it'll do this. When they have no understanding of HPC, they have no understanding of hybrid systems, they're vaguely aware of big data, and it's like, what's the ROI? Why should I give any more money? You already have resources. And you have to be able to explain it in very simple terms. They go, oh, okay, I understand that. And they'll give you, $500 million. And here's 5 years to go do this and keep it going. And then from contractors, it's like, okay, if you think of the days of video cameras and unmanned aircraft. So I was there when we put video cameras on unmanned aircraft and automated it. So now we call them Predators. But I was there when we first started all that. And video cameras weren't supposed to go on aircraft. Aircraft weren't supposed to be automated. But we did that. So big data, HPC, and analytics are all in those stages of being grown. And when you get them to where they're a little more mature and you start doing crazy things with them, you're going to have an explosion in capability. So we're a few years away, but it's coming. And that's going to cause it to go sideways in ways that we haven't thought of before. So I need visionary companies that say, here's your IT infrastructure. You got HPC over here in the heavy nodes, you got commodity over here, you got stuff in the center. I can deploy it forward with my heavy data. I can't put over the pipes because it'll choke it. It's just another node, remote. I can access it, I can look at it. If I wanted to pull it. But it has to be flexible. I have to put a new capability without breaking what I got, and I got to move it forward in time. That's what I'm looking for.
Okay. Shane, perhaps you could tell us a little bit about how you see the gaps and what's critical for you and missing.
Sure. So natural language processing is something that we're starting to look at for pre-screening and pre-testing to be able to take information from doctors' notes and things like that in order to put that into our analysis pipeline. It's very, very early stages, and it's a very hard problem to actually to get right. So something else, genomics and the medical record, with the size of data that you get out of a DNA sequence, and even the variant calls that you store, is very large, and most people don't know how to integrate that into the medical record. They right now just kind of throwing their hands up and scratching their heads. We've all heard talent is something that's lacking, but in our particular space, we're lacking talent on the big data side, because big data and HPC. HPC talent is very very rare, really. And then on past, once the analysis is done, you have geneticists who have to look at this data, and they have to sift through a lot of data. Even after we give it to them and we've pared it all down for them, it still takes a lot of time, a lot of their effort, and there's not very many great geneticists that can do this, and especially in the clinical space. So post big data, you know, we need people to be able to look at that data and make the diagnosis. So, which kind of brings me to my next point is we need to be able to have automation in order to pare that data down even further to give the analysts less data to look at. We need to help that with, say, machine learning, and even simple automation can do that. It's just a matter of man hours and the expertise in order to make that automation process, you know, reality. We also in the genomic space have a rough time deciding on what data actually needs to be kept permanently. I think we have a pretty good handle on it. Jack and I were having a conversation yesterday, I believe it was during lunch, where we talked about, you know, do you keep the image files, do you keep the raw data to go back to in case something blew up during your analysis. And we think that we've come to the realization that we have so many eyes on that data and all of the different steps that we go through that we probably don't need to keep it, but there's always that thing in the back of your head, maybe I should have kept it that time. So that's something that we always kind of battle with, because it's expensive. It's expensive to hold on to that data. It's expensive to back that data up. It's expensive to retrieve that data. It's just one of those ongoing things that we deal with. I think that's probably about it.
Can I make a comment about his last problem?
Sure.
So we've come up with a new technique where we have say like one of these floor tiles, three-dimensional collect, and we've come up with a technique to desiccate like 10 to 1, 100 to 1, the stuff we don't care about, and leave these spots we do care about. The background that's been desiccated or decimated is just there for context. And then you highlight the areas that you leave are fully populated and carry that whole package. And it reduces your data load maybe 100 times. So you have the advantage of keeping the entire background of what you collected from maybe multiple views, and only highlight the anomalous structures. You guys might think about anomalous cell structure, and retain that. That would cut down what you would have to say.
Jack may have a different idea, but that's probably a VCF or I mean, but we really have to keep certain files, certain large files, say FASTQ files, that we would be able to reuse in order to recreate that VCF if something did go wrong, or if we needed to revisit it.
Well, we have the same problem with some of our raw data is in the smallest format, or smallest, densest format, and once I start touching it, it conflates 10 times, 20 times, 30 times. So I keep my raw data in certain objects.
Yeah. Part of the things that we have are legal
Yeah, yeah, exactly.
That you have to have the provenance of everything. What is that decision that you made? Because if I treat you with a particular drug for the tumor that you have today, I have to prove that I had best practices and did all of my due diligence, just in case. And that's just a requirement.
Also in academia, I mean, you have to have that data in order to back up papers, and you have to be able to publish that, publish that
You have
data.
different requirements.
Yeah, yeah, for sure.
Yeah, some of mine are transitory. Tomorrow that whole scene's going to be different.
So Gary, maybe you can talk a little bit about the mobile world and how you see, how will big data be used? What are the technology bottlenecks in using big data through, mobile devices?
Yeah, sure. Big data is a big challenge for mobile, but at the same time, big data is an opportunity for mobile. These days, on lots of mobile devices, particularly on smartphones, there are over dozens of types of sensors. So each type of sensor will have a unique format of the data that coming out of it, and how to handle all types of different sensors, the format, the sampling frequency, going to be very challenging. And I think this is going to be involving lots of different shareholders in the ecosystem, because the sensor vendor needs to be understanding what kind of application the sensor is for, and think about the specific characteristic about the design, the testing, manufacturing of the sensors. So lots of times that the sensor company and the foundries and even the operating system providers, the OS, either Android or some other OS providers, need to work together to get a very efficient sensor solution in place. So when we have the sensor, then we can have the data. So there is big data topic. So I think most of these challenging gaps now for mobile on big data actually is one is how to efficiently collect these different types of data, and how to use a good algorithm to further process it. And because mobile device many oftentimes is with a compact format, and power consumption is very critical. So a good power saving strategy is always with high priority. So both on the hardware side and also on the software algorithm side. So we need a good algorithm that can handle the sampling and further processing of this data in the right way, and try to reduce the central CPU's load as much as possible efficiently. For example, lots of batching algorithm are in place, and we have the interrupt, as little as possible, so you don't have to, wake up the central processor many times during the process. Those are some things that we see some solutions these days, but we definitely would like to have a reliable, power efficient, and also reliable solution to collecting all of these different type of sensors. And there is always trade-off. That is, you cannot have everything just at one time. So strategic thinking is very critical. In terms of some of the opportunities for mobile, I think this is tremendous, because mobile device these days actually attached to every single person. And the world is connected, not only device connected to people, but also the device is connected to device. Lots of IoT topics, machine to machine, and also lots of smart home applications, smart vehicle applications. These are all under the same umbrella. That is, how are you able to communicate with the other connected entity efficiently? That's going to be under the same challenge for us. I guess in the near term, we probably need to identify some of the good standard. Standard means that could have all the industry leaders coming from different backgrounds with different expertise to put a standard in place. So this could speed up the process of adopting different type of sensors and different type protocols for the connectivity at your home, when you are driving on the road, or even, connect different cities through different efficient ways. And also, meanwhile, I think security is always cannot be overemphasized, especially these days. There are lots of wireless connectivity, different protocol involved. Either you have a Bluetooth or Wi-Fi, Bluetooth low energy, Zigbee, so on and so forth. Security is so critical. We don't want lost any data. We don't want any unauthorized, party to take advantage of this gap. So those are a few things that I think lots of good vendor, lots of good solution providers working on it, and we are actively working them together to get all the pieces, optimized to, improve next level total solution.
Great, thank you. Ron, you have kind of an interesting perspective. You see a lot of these HPC big data related projects trying to become commercialized, which gives you maybe an interesting window into both, the hardware infrastructure, the software, basic software, as well as tools and analytics. What do you see as the gap, or the gaps?
It's interesting, as each of the panelists went through their examples, they said, I have a project like that. I have a project that's sort of like that. I'm taking notes. I'm going to send Gary to this project, and so. But in terms of gaps, I see a number of different gaps. Some of them showed up in my talk. One interesting partnership that we're working with, and I failed in my talk to pitch our conference, so apology, Tom, I want to pitch our conference. But I have a partnership with one of the engineering schools in Toronto and an art school. And they're partnering together on data visualization technologies. And I think there's a big gap there in terms of visualizing the data and make it easy to consume and easy to manipulate by non-tech experts. So we're actually going to have a really big display at our conferences, April 27th and 28th. And they're going to come with large-scale interactive displays and displaying some of their research around the visualization of data. So that's a big gap area, and it applies across many industries. Anthony was talking about 3D imagery, for detection of subjects of interest, right? I have another partnership with a college that serves the studio industry, and they're doing all kinds of 3D imaging technologies for pre-production and post-production analysis in the studio industry, and I'm starting to cross-pollinate that with the medical industry and 3D imaging. The short clip of the video I showed you around functional MRI, they're now doing a project with IBM that will look at training Watson not to just process text, but to be able to process neural imagery and be able to learn from neural imagery and be able to, as Shane pointed out, try to automate some of the processes of collecting the right data for those specific patients in a timely fashion. So the whole area around data visualization, 3D tools, non-expert tools. I've got a project with a professor out of Western, he's a humanities researcher. He built his own graph analytics tools, visual tool, to track art communities' behaviors. It turns out that same tool can be used for fraud analytics. So I introduced him to our financial services forum. And so some of the banks are looking at the research. So there's all these cross-pollination areas. If we get down into the hardware and software, I have a number of projects around FPGA. I'm an old circuit designer, and when we did our startup, we put our IP in an FPGA, and our top designer basically said, well, FPGA, that's easy, that's just typing. But for a software programmer, IBM is telling us that this is one of the hardest devices to target in a software world. So we have several projects around, and there's a lot of work to do in terms of getting algorithms and applications onto an FPGA. It runs faster, it runs with a lot less energy, and there's lots of benefits to that. But that whole workflow in terms of algorithm development, there's lots of missing pieces there, and it has tremendous potential to speed up simulations, to speed up data analytics, and to conserve energy. Probably the only way to exascale, I think, is with FPGAs in the mix somewhere. And I'm sure there's lots of people looking at that. Had some discussion with some of the Univa guys, and we're building university data centers with HPC that has to serve the needs of batch processing for the guys that are running HPC simulations, but we're also getting more and more data analytics clients that need analytics processes that are more long-term processes. So running a Hadoop job on the same cluster as we're running a crash simulation, and how do we balance all those resources and all those scheduling requirements is a lot of new work that needs to be done there. Sharing an HPC cluster with the simulation guys and the analytics guys, those are a lot of new challenges there. So some of the gaps that I'm dealing with.
Okay. So I'd like to open it up to the audience if we have some questions around the gaps, the critical missing elements in big data. Any takers? I wanted to hit one point again. So we've talked almost entirely, with the exception of the FPGA discussion, about software-related issues. Whether it's analytics. Is there any hardware-related infrastructure changes you're expecting soon that will be impactful? So what are you seeing in that sense? Is there anything? For example, I know there's some effort to have specialized processes for the genomics world. What kinds of things are you seeing, sort of not just in software, but in the hardware world, whether it's storage or computational, that may have an impact?
I think FPGAs are coming back.
Yeah, they are. Yeah.
'Cause, we did a lot of work in the early 2000s on FPGAs, and it was hard. And the ecosystem wasn't mature, and I don't think that the genomics world, at least for us, was mature yet. I think that the algorithms are starting to settle down to the point now where you can put it in FPGAs and you can get an ROI. Before it was a research problem. But I'd like to pick up on one other thing. When we touched on security, but security is a huge factor, especially in the medical world. And one of the cool things when you talk about fraud detection or a lot of the other anomaly detection that we say is you've got enough data now that you can make a really good probability distribution function to know what your normal looks like. So you can determine what's outside of the norm, right? We need a lot of data in the medical world in order to do that. And because no one wants to really share the data, a lot of times the way that either the clinical trial or the hospital policies or whatever is set up, you can't share that data. And we need certain parts of it in order to develop what's normal. What is normal operating parameters for a human being? And we need the algorithms and to be able to share data while maintaining privacy to get the critical data that we need without exposing that it's John Russell has this problem at my hospital, whatever. But we still need to be able to have that data, and I don't think that technology is there yet. I'm still seeing it in the research journals. That's something that's going to come down the line, and that's something I think eventually is going to lead to an even bigger explosion of us being able to utilize and generate the big data.
Actually, that picks up right on the question I was going to ask, which is around governance and sharing of information, sharing data. I'm in an enterprise setting, and the problem that we have is lots of data in lots of places that is very poorly described, and there's no common language, there's no common framework, there's no way that one group in one division could even know about or access data in another division that would actually help solve the problem. So I don't know if there's an analog in the genomics world or elsewhere where they've solved this problem, but it certainly exists in the enterprise.
I mentioned it yesterday, data curation is absolutely necessary. It's a necessity. You have to know where your data is. You have to know what file types you're dealing with. And we get around that several ways. We have a LIMS, laboratory information management system that tracks all that stuff, and we've actually built onto it. It originally was developed at NCGR, the National Center for Genomic Resources, where the creators of the Center for Pediatric Genomic Medicine came from, and so they brought that LIMS with them, and it's able to track the data from when the sample was taken all the way up to where the data lives, what format it's in, and it's easily searchable. It's there, and it's in our particular area, it's all de-identified. So in that instance, it's secure, and so that's how we get around it. I mean, but it has to be curated. It has to be.
So from a curation side, we look at it as a veracity. Can I trust that data? We also look at the explosion of what we've been told to collect, from cameras in parking lots to phone cameras to cameras in buildings, any type of device you might take an image from, have a reading on. And I'm looking at using virtualization. Some of the sources are completely unstructured. Some of the sources I deal with are very structured. I also have to be able to expose the kind and quality of the data to a person looking for an answer of, here are the number of data sources you can query, here's the quality of the data, here's the resolution of the data, here's what you can do with, and that's getting very complicated. So part of what the compute infrastructure will be used for is managing those types of questions for the person making the query. And it can be across multiple agencies. It's a very complex management layer. Employing the right tools, the right curation, keep that data forever, throw it away, replace it with this current one. In that geographic area, we only have 3 data sources. This is the most trusted, but this is the closer one. Which one do you select? Do you select all of them? So I'm trying to build, in the future, algorithms that take all that into effect and supply the person asking the question with, here's what you got. And that's, you could approach it the same way, but one of the biggest things that even the medical community is, do I have all the complete data? Is it quality? Can I trust it? And then how can I use it to come up with an answer and then go back and review it?
Yeah.
I just wonder if we can backtrack on the hardware thread for a minute. I'm a hardware engineer, and it's the thing that excites me, and I really didn't have a chance to address that, so we've covered the FPGAs, but I think there's a number of other very interesting hardware technologies coming down the pipe. We're seeing all kinds of analog neural chips. There's one out of Stanford. IBM's working on one, and the video I showed you about the neuroscientist, he's written his code so that he can target it to any platform. He's run it on an array of ARM processors. He's running it on the Blue Gene now. He's actually targeting at the Stanford neural chip. So there's all kinds of really cool hardware technologies coming down the pipe. I've talked to folks in the studio industry. The studio industry is going 4K, stereoscopic, high frame rate. I think it's called light field array camera, so they have multiple exposures in multiple focal lengths all concurrently. They basically need to bolt a supercomputer on the back of a camera. In some cases, they just want to track the football in flight, but there's all kinds of applications for that. So that's a new hardware domain. Then they're going way out there. We've all heard the controversy around D-Wave and the quantum computer. Well, they've launched a software startup, and that's in our Toronto incubator, and we're looking for research projects to look at algorithms that will run on the D-Wave, and we're talking about a partnership with Lockheed to put some pilot projects in place for that. And if we want to go even further out, one of the BlackBerry founders, Mike Lizardis, put $100 million of his own money into the Institute for Quantum Computing at the University of Waterloo. And we're actually commercializing some technologies there about commercial volume, cheap, entangled photon sources. So there's all kinds of really cool hardware stuff coming down the pipe, and there's a lot of new work to do.
So you're talking about these 4K cameras. That's driving a lot of the technology on our imaging side as well, because you're able to take that. One of the things we're running into is basically you can now collect images to whatever depth that you want, to high resolution, but when you want to visualize it back and you want to do either information visualization or some sort of realistic visualization, most of our displays don't have anywhere near the dynamic range of the human eye. So we're losing a lot of the depth and a lot of subtlety that's there. So being able to take VR, and we're looking at the virtual reality types of things coming out, to be able to directly visualize that in a way so that you actually get back to that dynamic range and you can see in some sort of a realistic way what you actually would see if you were looking at it with the human eye, and even to be able to expand the range of what the human eye can see and be able to pick out more patterns, especially in the texture and everything else that we're going towards. So there's a lot more to be driven, and that human-computer interface is still a long way away from where we can actually take advantage of that and start seeing that. But to specifically answer the question that you asked, that's why one of the reasons why we're going towards graph analytics is we're trying to see whether or not we can search subgraphs that are similar to try to bring in really disparate pieces of information and then visualize that in a way that maybe that has something to do with going across these disparate data sources for data integration.
I think I was getting a high sign by Philip. Is that the correct?
I'm always the bad guy.
Very good discussion. I'm sure there's a few more questions, but I guess they'll have to wait. I'm interested to hear more about the hardware infrastructure, because we just sort of don't talk very much about it here. We really talk about the analytics that are running on them. How can they work together more efficiently? What do we see coming down the base? Quantum computing a real thing or not? A lot of things there that we could further discuss. But I guess we'll hold it off. So hopefully you'll have a chance to talk with all of the panelists at lunch. I know this isn't the conclusion, but I do want to personally thank everyone for what's been a fantastic conference so far. I think the conversations have been really terrific. I've enjoyed the folks that I have met for the first time, but honestly, I hope you've gotten something really fulfilling out of it, relationships that will carry on, new lines of thought that you will follow up on, and I guess we'll break for lunch. Is that right, Phil? I want to thank my panelists, too. Thank you very much. It's a very wonderful panel.